Hi, this is Sholey Physics APC Mechanics Exam Review number 1. We'll be covering vector scalars and kinematics in this session. First off, just to make it quicker, I'm not going to be typing stuff out and listing a whole bunch of stuff. I'm just using an old review packet I used and going through it, just annotating as I go along. Down in the description of this video, it's going to be a link to this document you can access anytime. If you'd like to just look at the document instead of listening to me go through it, that's great. So here, just starting out with all the different quantities in APC mechanics for mass, time, speed, distance, position, work, potential energy, kinetic energy. All these are scalar values. The units are given here if you need to look those up. They're also on the equation sheet and table information that comes with the APC test. Symbol that I'm using in this review, all those symbols are over there. So all these are scalar values. They don't have any direction to them, and some of them have vector buddies like speed and velocity are basically both meters per second, distance and displacement, like angular displacement, angular distance, if you can call it that. I don't like angular distance. This makes sense. Anyhow, we've got the list of scalars and vectors on this list. Here it is blown up, be more difficult to see. And there's a whole list. Down at the bottom, of course, we have moment of inertia is I. That is a scalar. I had left that off the original scalar list up top. But that should be a good resource for you to use if you're trying to remember some symbols, names, and such, and all their units that match up. Moving on to the next page. That was unskillful. Here we go. That is more skillful. There we go. So all about vectors. Vectors can be added and their components can be found. So if we have vector A going to the right and vector B going up, there they are. How would we add them? A plus B. We add them by taking their beginning and attach it to the end of the prior one. So A plus B would be vector A plus vector B. And the resultant is the vector A plus B. It's a hypotenuse of this triangle that we made. Now, not all vectors are going to be perpendicular to one another, so the Pythagorean theorem is not going to be useful for everything, but you, of course, have laws of sines and cosines. I prefer, if you've got two vectors, maybe one horizontal and one at an angle, and you're adding them, I like finding the components of that angled force first. It could be a force or angled vector, I should say. So you find that horizontal piece and then the vertical piece. Add the horizontal piece to the horizontal vector and just add up the horizontal components and then the vertical components after that. There you can see an example, a reminder about how to add those vectors together. But this part in the bottom is finding the components. So keep in mind, if you have something like a force of 20 newtons, the x component of that force would be 20 cosine 40 in this case, and the y component would be 20 sine 40. That's handling vector addition and finding vector components. Moving on to the next page. The dot product, also called the scalar product. Let's zoom in on that. Use the dot product if you're multiplying vectors together when the parallel components matter. The parallel components using I notation, I dot I is 1 and I dot j is 0. So recall that the I is the x direction, j is the y direction. And here's our example. How much work is done by a force to displace a box? So in the case of work, if you push down on a box, it's not going to move the box, but that pushing force will only be effective in its horizontal component. So its horizontal piece is what's going to displace it horizontally. So in this scenario, work is the product of force and displacement, both of those being vectors. So we're going to take the dot product, the scalar product. And the result that we're going to get out is directionless. It has no direction. So that's why it's called the scalar product. Definition of the scalar product is right here. A dot B cosine theta is the dot product, and that will give you the amount, and that value doesn't have direction like I said before. So this is only a magnitude. So if our force is 20 newtons and our displacement is 10 newtons, we're going to take a 20 times 10 times the cosine of the angle between them, cosine 30. 20 times 10 cosine 30 would give us 173 joules. Now that's not, that's more specific to the work unit. It's just a working example of when and how to use the scalar product. Just as another note, if you look at this 20 Newton force, we find the adjacent component to the angle. That would be 20 cosine 30, and that's what we're multiplying here. This 20 cosine 30 is that component of the force that is parallel to the displacement, that delta x there. So that 20 cosine 30 is just another way to look at this. We're multiplying that parallel component of the force to the displacement. Moving down to the vector product. We use the vector components or vector product when it's the perpendicular components that matter. So we approach this when talking about torque. To turn a wheel, make it spin around, if you push inward toward the radius, it's not going to spin. There's still going to be zero torque applied. It's only when the force is perpendicular to that radial vector, that radius vector, that's when you get a torque. So to calculate torque, we take the radius vector, cross it with the force vector, and this will give us a direction of spin also. So this is called a vector product because it has a direction. I cross I, those parallel components cancel. They won't do anything, it's zero. But I cross j gives us k. And I give a method here of working this out. What would, for example, j cross I be? Well, if you go j cross I, that would be k, but toward the left in this little tool gives us the negative. It would be a negative k. J cross I is negative k. What about k cross I? K cross I would give us j with a positive. It's going in the positive direction. K cross I is positive j. And that's how you can work out those components when you're doing a vector product. Now the definition of vector product is over here, A cross B. And this would be the magnitude of A cross B. Of course, it doesn't have a direction given here. You'd have to figure out yourself. A cross B is AB sine theta. It's the A sine theta gives us the opposite component, the perpendicular component, comparing to the angle between vector A and B. So we take RF sine theta would be the torque applied to that wheel. Now as far as direction, you take your first vector, which would be up, and using the right hand rule to go up, and let me see myself here, I can't view myself, there we go. So I have to go up and cross it with, oops, going opposite, there we go. Take your right hand up and cross it with the force. So that means the direction is out of the page. It's where my thumb is coming, okay, where my thumb is pointing there. Okay, so that gives a rotation in that direction. All right, I like using the thumb, the right hand rule in this case when it's dealing with spin, like I'm holding a mug. So if I have the rotation R and I hold my mug in the direction of F, then the rotation is going to be counterclockwise, positive. Okay, and that'll make that bike wheel spin just like that. All right, so moving on, our next page. We're introducing kinematics quantities here. So average velocity as opposed to instantaneous velocity, we'll have it here. But average velocity is a finite, a defined amount of change in position over a rate of change in time. So this is a rate, how quickly displacement changes, how quickly position changes, where acceleration is a rate of change of velocity, how quickly velocity changes, and that's also with finite amounts of velocity. Now if we take a position time graph and look at a plot of a position of an object over time, we see that the position is changing, and also the velocity would be changing. Here you might recall that positive slopes here gives us a positive velocity, negative slopes gives us negative velocity. The degree of the slope gives us the amount of speed. Okay, but if we if we look at the whole thing, there's a lot of different velocities. We could take the overall displacement on this graph from beginning to end might be 0. If we look at the starting position and the final position, there's a starting position there and the final position. They're all about the same position. So the average velocity of this motion may be 0 if we look at the entire time. Or if I look from the beginning to the top point up here, the average velocity would be this point minus this point. That'd be the displacement divided by the time interval there. So that might not be very helpful either if you're trying to actually figure out the velocity at a certain instant. So if we zoom in on that little point, the slope is something like this at that little point, and that's what the dx dt represents. It's a very infinitesimally small interval of time, which would give us a very infinitesimally small change in position, and that's what would be the instantaneous velocity. So the velocity is the time derivative of this change in position of the displacement, where instantaneous acceleration is the time derivative of velocity if you have a velocity function like that. So continuing on, where do we get the kinematics equations from? Well, first off, we need to remember something very important here, and this is a gotcha question. It's not really a gotcha as intended, but you really have to be on the lookout for this. On the AP test, if you are given a question that has an acceleration, but you're unsure if it's constant or not, or if it gives you a time-dependent velocity function or a time-dependent acceleration function or even displacement that's like a t to the third power instead of a squared, then you're not dealing with a constant acceleration. So be sure to not let that get you. But if you're absolutely certain that we're dealing with a constant acceleration, we're going to start with that definition of acceleration, a equals dv dt. We bring the dt up to the a, and that leaves us with a dv equals a dt. So dv equals a dt. And that sets us up for an integral. And if we integrate from some starting velocity to some final velocity, there's a start to the final, then on the right side, we're going to integrate from the starting time t equals 0 to some arbitrary time t later on. Integral of dv is v, and we take the final v minus the initial v. That'll be on that side. And if we integrate this side, a dt with respect to t would give us a times t, and we take the upper and lower bound, gives us a t minus 0 in that spot, and rearrange, add a v naught to the other side. We get our first equation of motion for constant acceleration. Now, if acceleration is not constant, if acceleration depends on time, then you can't use Vf equals V0 plus AT. The average velocity during that time it's accelerating is not a constant. So that's an issue. Therefore, you got to integrate. You got to go to the integral. If a of t equals 2t, we integrate and we get Vf minus V0 equals t squared. And we get a different looking little creature here. But also notice that initial velocity is still there. You can't forget that. Consider that initial velocity. Usually in a problem like this, it'll give you the initial speed, or you might say it starts at rest and then undergoes this acceleration. So oftentimes this is 0. But note that we have to do this. You have to do this for a non-constant acceleration. Very important to consider there. All right. So moving on, we have Vf equals V0 plus AT. It's one of our key constant acceleration motion equations there. But what else can we get from this? Well, starting with the definition of velocity over here as a time derivative of displacement, if we plug in that v0 plus at as our v of t function and integrate sort of how we did before with the velocity function, we get an x final position minus x initial, and integrating this side, we get a v0 t plus 1/2 at squared. So that should hopefully sound very familiar. Here's our second equation of motion for constant acceleration. Now these two are very useful on their own, but they are both time dependent. Time dependent. So if you need a tool to use that is time independent of time, if we combine these two expressions, set this one equal to t. So what does t equal here? Vf minus v0 divided by a. And if you plug that in here and here into the second equation, we have a system of equations, you'll end up with the third equation after some ugly looking algebra. You do get that third expression, and it's independent of time. So those are your three tools for constant motion, for constant acceleration. We use these especially for objects undergoing constant acceleration, which includes objects in free fall and projectile motion. All right, this is one more example. If you've got a velocity function, what is the displacement and acceleration function? So first off, to find a displacement, you'll rearrange dx over dt. So you have dx equals v dt, just like in the previous example with non-constant acceleration. And you end up with integrating 2 minus 3t cubed, and you get the funky looking displacement down here at the bottom. Okay. Now to go the other way, what if you want an acceleration? Well, an acceleration is the derivative of the velocity function. So we're going to take the time derivative of t minus 3t cubed. Derivative 2 is 0, and derivative of negative 3t cubed is negative 9t squared. And so you'd have that result as well. All right. Moving on, we have our toolbox now. So let's do some, we'll get to the graphing part in a moment. If you're wondering about the graphs, don't worry, it's coming up. So to note, these are all good for constant acceleration. These are only for constant or zero, constant motion or zero acceleration. And I've got a couple reviews of those definitions here. I'm working off a couple of my packets that I did, so some of this might be a little bit of repeat. So when you're approaching linear motion problem solving, just keep this list in mind in your head. This helps you reduce the chance of accidental errors. Number one, as you see a problem, toss a ball up at 3 meters per second from a height of 1.5 meters. What's the time to get to the highest point? What's the maximum height? And what's the time in the air? There's a lot of things we can figure out. This actually leads really well into projectile motion, but this is just a linear motion, toss a ball up kind of question. First, you'll probably have a more developed question than this, but when it comes down to it, begin by writing out your givens, the implied information, and the target value. So these are the targets. That's what we're looking for. What's given is 3 meters per second, and we're going to label that. So initial velocity is 3. It says it's tossed up from a height of 1.5 meters, so that's a starting position. X0 is 1.5. And we're looking for the time up and the maximum height. So we should also think, maybe draw a little sketch, that sometimes helps. Here's a little sketch. The velocity at the top is implied. What is the velocity at the top? We have to figure out the maximum height and the time to go up. So we're going to have to know what do we know about that maximum height? So velocity at the top of an object tossed up, and when it falls back down, that maximum height velocity will be 0. The other implied piece of information always is, we're assuming this is on Earth, so gravitational field of Earth is negative 9.8 meters per second squared, and that's a downward acceleration. So writing all that up writing all that out, just lays everything out in front of us, and now we're ready to solve. Next, we're going to select an appropriate equation of motion to use. First, let's consider, is it constant acceleration? If it's not constant acceleration, we're going to have to do something like this or that, okay? But since it is constant acceleration, we can use our equations of motion. All right, so which one's going to be most appropriate? Well, first, to find the time up, the time in the air, what we do have is a starting position, and we have a final velocity. We don't have a starting velocity. You see that? Oh, yes, we do. We do have a starting velocity 3. There it is. So great. So we have a starting velocity. We look for time. We have a final velocity, and we have acceleration. So I might pick to use, let me zoom this out a little bit, make this more usable. We might pick to use VF equals V0 plus AT. It has all of them. That'll give us the time to get up, the time to move to the highest point. Next, that makes it easy to solve for the highest position. Using the second equation, what is x? The initial position is 1.5 meters. We have the initial velocity of 3. We have the time to go up, and the acceleration time to go up there as well. So we can figure out the x. And that's the first two sections of that solve. VF equals V0 plus AT, plugging them in, and then zoom in down here a little bit, and then using x equals the 1/2 AT squared expression. Okay, there it is. And finally, we need the time in the air. Can't forget that. Always look back at the end. What is the total time in the air? So the final thing we need to do, we've got the time to go up, so we need the time to drop down to the ground. So that becomes a third problem with an initial velocity of 0, but we don't know the final velocity. However, you do know the height at the end. So you might apply that x equals x final equals x initial plus V0t plus 1/2 AT squared. But now we're starting, our time t is starting at the very top. So the initial velocity at the top is 0. We're accelerating downward, trying to figure out the time down. The final position will be the ground. The initial position is what was solved for as the maximum height. So plugging all that in, we get a solution of the square root of 0.4, which I suppose is 0.632. And we add that to the initial time up to get the total time. So that's just an example. Moving on to projectile motion. When you're solving projectiles, keep in mind, unless it specifies some other planet where you figure an acceleration due to gravity, our acceleration is going to be 9.8. When we're dealing with projectile motion, keep your horizontal data on one side and your vertical on the other. Keep it separated. I can't stress enough how many people make mistakes by putting a horizontal velocity in the vertical side or in a vertical equation, or the vertical drop distance. They're thinking it's a range. Keep your data separate. The only thing that can crisscross is time, because time is not a vector. It's going to flow no matter what direction you're moving in. It's going to flow the same. So this is an example. The pumpkin is chunkined with a speed of 100 meters per second at an angle of 42 degrees above the horizontal. It means it's fired. You ever heard of the pumpkin chunkin competition? I think it's in Pennsylvania. Go Pennsylvania. I'm actually from a different state, but Maryland. Go Maryland. All right. Anyway, here we have horizontal data on the left. We get the vertical on the right. It's always good to consider the horizontal velocity as a component of the starting velocity. VH equals V cosine theta. And here's the vertical, the initial vertical. So something to remember in projectile motion is the horizontal motion is always constant, while the vertical motion is accelerating. So constant velocity for horizontal, constant acceleration for vertical. If you're given the initial speed and angle in the problem, go ahead and solve it out. What are those components going to be? There I did, solved them out. If you don't have them, keep it as V sine theta and V cosine theta. Plug in the theta if you got it. Don't plug in the theta if you don't got it, depending on the question. From there on, how do we solve the problem? It's not too bad. What's the time up? The time up is equal to the time down. Here's a little graphic in the bottom. So if you got the total time, and we're working with a nice horizontal flat ground, the time it takes to toss the ball up is equal to the time it takes the ball to come back down. So the total time is twice the time up. Well, how do you get the time? It's actually better to start with the vertical. At the top, to get the time up, remember that final velocity at the top is 0. So if we have a final velocity of 0, an initial velocity of not 100, but 66.9, this is where people sometimes mix up those numbers. So don't do that. Keep them separated. So I take the final vertical velocity at the top, the initial vertical velocity at the bottom, the acceleration of negative 9.8. You can solve for the time up, or the time to the top, right there, 6.83 seconds. Well, since the time up is 6.83, the total time over on the horizontal side is going to be 13.66, just double that. So why is that on the horizontal side? Because that's how long it's going to take for that projectile to go up and down. I'm just reviewing the basic projectile problem. Hopefully you're picking up on a lot of these implied values and things like that. But just to keep everything together, keep them in the horizontal and the vertical. And finally, if we take x equals v0t plus 1/2 at squared for the horizontal, but keep in mind in the horizontal direction there is 0 acceleration unless there's some air resistance. And mainly if you're doing a projectile problem, there's not going to be air resistance. So the 1/2 at squared term drops out and you're just left with x equals v0t, and the v0 is the horizontal velocity the entire time. So we're going to plug in that horizontal velocity now. I'm having problems with my highlighter. Plug in the horizontal velocity times the total time, and that gives us the total horizontal range. And finally, the last thing we can figure out is the maximum height. So maximum height deals with the time up. So we can use x equals v0t plus 1/2 at squared right over here. Plug in the initial vertical velocity, the time up, the 1/2, a is negative 9.8, and this is a time squared. Okay, there should be a squared in there. It's probably off my copy. But solve for that total, that maximum height. Basically, 66.9 times 6.83 would be a larger number than 228, but it doesn't continue at that constant speed because the projectile is moving with a negative acceleration due to gravity. So it doesn't go that far. We have to subtract some displacement due to that negative acceleration. So that's solving a projectile problem. All right, now moving on. We're almost done here. Graphs, motion graphs. When analyzing any graph in this course, I've got a sample of a velocity time graph here. Number one, think to yourself, what does the straight up data reveal? All right, in this graph, this data reveals that the velocity remains constant. It increases, so it's getting faster. It stays constant again, but non-zero, and then decreases at a changing rate because, well, we're going to get into that in a second. It just decreases here. So that's what the data reveals. It's not what the velocity is doing. Next, consider number two, what does the slope reveal? Well, the slope of velocity time graph is the y divided by the x, velocity over time. So change in velocity over change in time, the slope reveals acceleration. That's the definition of acceleration. So on a VT graph, think, what does the slope reveal? V over t, that's acceleration. So a zero slope means zero acceleration. It's not getting faster or slower. That agrees with what the data reveals, that the velocity stays the same. Here the slope is positive and constant. So this is a positive constant acceleration. Here the slope remains zero again. It stops accelerating. And here we've got a negative slope, so there's a negative acceleration. And that slope is steep and it's lessening. So there's a large rate of negative acceleration at first, and it begins to decrease that rate of acceleration because the slope is decreasing its slope. It's becoming less negative and more positive. So we actually have a positive jerk here. Jerk is the rate of change in acceleration. This course doesn't cover jerk, so I'm not going to be a jerk and talk too much about it. Moving on to number three. What does the area under the curve reveal? This is the third thing you should think about. So what does area tell us? Well, area that's under this curve here. Does that have a meaning? Well, if we take just a block, maybe this block over here, let me erase my area. What if I just take this block of area? It makes a little box. And if you multiplied the sides of that box, you get an area. Well, this side of the box over here is the velocity side. And this side of the box down here is the time side. So what's velocity times time? That's equal to displacement. So the area under the curve, the third thing, is displacement. So if I add up all the area under this curve, I get the total displacement during that entire time interval. All right. So what does the data reveal? Velocity changes. What does the slope reveal? The acceleration changes. And what does the area under the curve reveal? The displacement. And finally, if a particular problem gives you mass, also, number 4, what if mass is known? What also does it reveal? Well, if you've got velocity from number 1 and mass, you could also figure out momentum. You could also figure out kinetic energy, 1/2 mv squared. Momentum is P equals mv, right? Those are a couple things. Maybe there's more. What about slope? The slope is acceleration. So if you also have, number 4, if you also have mass, what's mass and acceleration? Force. Mass and acceleration is force. If you have force and time, maybe you can figure out impulse. Change in momentum from there. Whoa. And how about area? Area is displacement. So with mass and displacement, don't think you can figure much out from that. We're not talking about balancing an object. So you might be thinking, well, mass and displacement is center of mass. Well, we've got a moving object here, so that doesn't really work here. It's center of mass is more of a length rather than a displacement x. So don't confuse that. So mass and displacement doesn't tell you anything, but mass and acceleration does, and mass and velocity does. So having mass under your belt reveals a whole lot of extra good stuff. These are a couple of examples here. When you're thinking about an xt graph, what's the slope reveal? That's the velocity. When you're thinking about a vt graph, what's the slope reveal? That's the acceleration. What's the area reveal? That's the displacement. And if you do have an acceleration time graph over here, what's the area reveal? That'd be a change in velocity, right? A times t would give you a vf minus v0, a change in velocity. Does the slope reveal anything here? Well, it kind of does, that quantity called jerk, but I promise not to be one, so I'm moving on. This was from my other packets, another good visual. Keep in mind area can be calculated if you need to with some squares and triangles. Area of a triangle is 1/2 base times height. Of course, area of a rectangle is length times width, or base times height, whatever you want. To find the slope, it's a change in velocity over change in time. Just think about those as you're going through this. You might like this list a little bit better. It's a little cleaner in some cases. In this course, you might have xt graphs, you might have force time graphs, you may even have power time graphs, or this could also be momentum time graphs. What about force and displacement graphs? The area under that is work done, F times X. Okay, so there's a lot that might pop up, but just consider those 4 things. What does the data tell you? What does the slope tell you? The area, and if you know mass, does that tell you anything else? That brings us to the end of our session number 1. Beat that on timing. AP Central. Their videos tend to be kind of quick, or really long, like an hour or something like that. But I'm just babbling along here. I hope this is helpful. Good luck on the test. Session 2 is coming up. Review session 2 is coming up.